Well, greetings, Mr. Kolazar's forensic science classes. What we're going to look at is kind of some introduction to blood spatter. Now, unfortunately, we're not allowed to use real blood. We have to use simulated blood or synthetic blood. So it's not real blood. If we were to actually use real blood spatter, or if you're getting authenticated in blood spatter analysis, you actually do have to use real blood, but we only are able to use a synthetic kind. So we're going to start off with what are known as passive drops. Now, blood has two forces of attraction. We've got cohesive forces, blood wanting to stick to itself. So it wants to hold together, so as it falls through the air, it kind of makes a teardrop shape and wants to stay stuck together. And adhesive forces, blood wants to stick to other materials, whether it's clothing, whether it's a wall, whether it's the ground, whatever it might be. So our first example we're going to look at are what are known as passive drops. Passive drops are going to be blood droplets that fall straight up and down. They fall from a 90-degree angle straight up and down. This allows them to stay in that teardrop shape as they fall, and when they hit, they should make a circular shape. So what we're going to do is examine those heights. There are different heights that they fall from and what it actually looks like as they hit the ground and what it looks like afterwards. So we're going to start out dropping. We're going to start from about 2 feet or a foot and a half in the air. We're going to then move to a little bit higher, maybe about 3 feet, about 50 centimeters. We'll move up higher, about 4 feet, getting closer to that 100 centimeter mark. And we'll move up even higher. And then we'll see if I get way up tall. And now what we're going to do is we're going to come in close for a little examination of what those drops actually look like. All right, so now as we observe the drops from up close, we notice that there are two drops very similar to each other, almost on top of each other, but they're circular in shape, showing that they're straight from above. Now notice from that 1 foot, around 30 centimeters, that they're a little under 2 millimeters in length there. So what we're going to look at is there are some spikes and satellites projecting around, and that's one of the big focuses we want to look on. So as we move to the 2 foot one, we can start to see that size-wise, it is a little bit bigger. It's still under 2 centimeters in length, but now we are starting to get more satellites and spikes, or mostly spikes, protruding out from around it. We're going to jump over to the 4 foot one. Our 4 foot one, now we're starting to really see a little bit of growth, but still, again, we're not getting a huge amount. Now we're at about almost 2 centimeters in length, but now we're starting to see a lot more of what we call our spikes and our satellites, where the blood droplets are actually starting to push out from there. The cohesive forces, the blood wanting to stick together, now the force of gravity is actually pulling it apart. As it hits from acceleration, it's causing more force of impact, causing that blood to actually spatter out a little bit further, showing that higher drop of blood. And our last one here, we got up around that 6 foot mark, around 180, maybe 200 centimeters, somewhere in that area. We can see now that the blood is around 2 centimeters again, or maybe just a little bit more with that width, but now even more spikes and satellites are starting to show up. That blood, as it drops, you know, maybe this is a case from a bloody nose or something, the higher up in the air that it goes, the faster it falls, the more acceleration of gravity, the more those spikes and satellites start to show, so we can use that to determine the height that the blood dropped from. So continuing with our passive drops, instead of those drops dropping straight down, we're going to keep that dropping down motion, except the person is going to be moving at the same time. So if we have a victim who's been, you know, cut, bleeding or something, and as they're walking along, they drop, the blood drops, they're still dropping down, but there's some movement involved. So when we look at that, we're going to start out in the person as they're bleeding, and then they're going to start moving across. Now that person also could be moving a little bit faster, so we could start that bleeding and then move faster, or we could even further go, start that bleeding, and then go really quick across. So now what we're going to do is, thinking about Newton's first law of motion, when that blood is falling, not only is it falling straight down, but it's got some forward momentum to it and that motion. What we're going to look at is how those spikes and satellites are different and how we can use that to track the motion from those blood droplets. So let's move in and look at those a little bit closer now. So upon examining this blood droplet, what we can see is that most of the satellites are now pointing out into that direction. So what it's showing is, as what we were saying, Newton's first law of motion, when that blood droplet hit, it actually kept moving forward slightly, and it shows that direction of movement, that it's actually traveling to the right or into that direction. So those satellites are moving, and what we can see is as we go to those other drops, that all of those satellites helping project, showing that direction of movement of which way that victim was actually traveling. So all of the satellites, those spikes, as they show our direction of movement, and we can actually use that to follow the path that the victim had taken, so that they can actually be used to follow all the way through. So that's our example of passive drops, but passive drops that show some directionality of movement. All right, so now as we continue, we're going to look at blood spatter, but we're going to include directionality. So with that directionality of the blood spatter, it's really difficult to actually take a blood drop and throw it at an angle and have it consistently land. So instead what we're going to do is we're going to drop the blood droplet straight down, but we're going to change that angle of impact that it would be hitting instead, so that we can actually mimic that blood droplet going sideways, but instead down to make that angle. So we're going to just look at a few different approximate angles of what blood looks like as we start to change those angles. And now that we've looked at blood changing those angles, we're going to come in closer to examine what we're looking at when those angles are made. All right, so now that we've created those blood droplets, we have this equation that we could use. The angle of impact is equal to the inverse sine, or sine to the -1, the width divided by the length. And a couple key things: width, remember, is always the wide or the smaller number. Length would always be the longer number or larger number. And then we don't measure the tails when it actually comes to that. We'll see that in just a little bit. So to begin with, we have down at the bottom here our shortest, our smallest of our angles being at the 90 degree, or like straight up and down, and then our 10 degree with our traveling over impact angle. And what we'd be measuring is the width of it divided by the length of it. And now as we're moving, we're going to check out 20 degree angle. We're going to notice that it's slightly a little bit longer, but the width is staying about the same. The length is what's increasing really. And as we move to 30 degrees, we can start to see the width increase. The key is, as we're working here, is we start to see these tails start to form. These tails, what we're looking at, we don't want to include in our measurements of those lengths and of those widths. So we'd be measuring those up to 40 degrees. Now we're starting to get kind of a tear or tail. We don't want to include that in our measurements, but our length and width divided by length. So we can see that the length is getting much longer, the width is staying approximately the same. Then we get to our really sharp angles. We've got now our 50 degree angle and our 60 degree angles. Again, we don't want to include those tails in our measurements, but they keep elongating more and more, showing an extreme or a sharper angle of impact that those blood drops are hitting at. Up at 70 degrees, we can see a longer length. That width is staying approximately the same. At 80 and 85 degrees, again, we're getting a longer blood droplet with that width in place. So by being able to see these teardrop shapes, we know that a directionality of the blood had to come from an angle, and we can use that equation, inverse sine of width divided by length, to give us that approximate angle of where the blood came from. We're going to be using that now to start into triangulation of where the origin of the blood came from. So now what we're going to look at is blunt force trauma. One of the ideas is this is going to be a low to medium impact that we're going to be looking at with the blood spatter. We've got our setup here with our sledgehammer and our victim, and what we're going to do is give it a little hit. All right, so looking at our low to medium splatter angle, what we saw was this is, we know where it impacted, but in the future you wouldn't have the known where the impact, we'd have to find that impact. So what we're looking at is we've got different little hints that can help us out. We've got some blood droplets here that are making those oval patterns and directions, and the tails pointing the direction of where they're headed. So we know that they are actually coming from that direction. Or if we look up ahead, we've got some of those droplets showing that they're headed in this direction from that tail, so they must have come from down somewhere else. If we can start to gather or string together a bunch of where they're heading and where they came from, we can start to figure out an origin. Or if we look down below on the blood droplets, we can see a lot of the spatter pattern and the direction that everything is heading by those tails and the direction that they're heading. So all of that must have originated or given us a point of origin that we're actually looking for. So we can actually use this to start to triangulate where the blood actually originated from a medium to high or medium to low impact angle. If we were to see a high speed or high velocity force impact, that'd be much more like a bullet or a gunshot wound. We don't have that ability to do that today, but what it would look like is something similar to a misting spray spraying out or projecting outwards. And so this would be an example of high speed where those cohesive forces holding the blood together have broken completely apart, and you can still see that blood directionality in the way that those blood droplets are going, showing the direction of the blood, so we would know that the origin was somewhere previous to that point. So our high speed spatter versus our medium to low speed spatter, using that to triangulate or to find out where that blood originated from. The next version we'd like to look at for blood spatter is the idea of castaway. Castaway would be if we had a suspect who actually had, say, a knife, and after that first attack or whatever it might have been, has had blood on the knife, and as they go to move it a second time, that actual blood actually flicks or casts off, and then as they go to repeat and then move back and repeat and move back, that blood is actually cast off of it. What that actually would look like is that every time that is flung back, that you'd get a trail of blood and a sharp fine line with those tails and arrows pointing the direction of which the blood is traveling, which is traveling. So in this case, this blood spatter would actually show that 3 different incidents of castaway where the knife was pulled back 3 different times after it initially had blood on it. So this is an example of what we're going to say is castaway blood spatter. Arterial gushes is going to be another form of blood spatter. An arterial gush is an unfortunate event where an artery is actually cut instead of a vein or capillary. Usually when we bleed, blood just kind of oozes out from a cut or a wound because we have not cut an artery, instead it was a capillary or a vein. However, when you cut an artery, every time your heart contracts or beats, it actually forces the blood or squirts that blood outwards through that artery. And so what you can see is when you actually cut an artery, that blood is actually ejected or squirted out. This is going to be a pattern, what we're going to call an arterial gush, in which the blood actually bleeds out, and then every time that heart contracts, it actually gushes more blood out, and every time the heart contracts, it would actually gush more blood out. So an arterial gush pattern we could actually see is indicated by those gushing of the blood every time that heart beats or contracts there. So this is our example here of arterial bleeding or arterial gush.